Hey everyone, I'm Jimmy Zelensky. Today I'm going to be talking about implementing strict serializability with pgexact. If you're interested in correctness and the internals of Postgres, this is a talk for you. Okay, let's get started. Today I'm going to give this talk, but I'm going to break it down into a couple of different chapters just to give everyone an idea of the structure of the overarching talk. Right now I'm giving you the agenda, but then I'm going to give you my bio just so you understand who you're listening to, why you should be taking these seriously, why anything I'm saying matters whatsoever. Then we're going to kind of give everyone a refresher if you're unfamiliar with what consistency is. I'm going to cover that at a very high level, hopefully enough for folks to understand it if they've never been introduced to the concept whatsoever. But it'll be mostly a refresher for folks that are familiar. Then next up, I'm going to cover what strict serializability is, which is a particular type of consistency that is the focus of this presentation. Then I'm going to cover why we at my company needed strict serializability and why you might need it. Odds are you probably haven't heard of it or needed it if you're uh, listening to this talk. So um, definitely needs covering. Then I'm going to talk about our initial approach at trying to actually get strict serializability out of Postgres, how we implemented it at the beginning, and then where we arrived once we discovered pgexact. And then I'll kind of cover some of the trade-offs associated with how we did it and kind of give conclusion on that. So, who am I? My name is Jimmy Zolinsky. I am the founder of a company called authzed. Authzed builds a particular type of database called SpiceDB, and that is specialized for building authorization infrastructure. So, our domain is explicitly designed around kind of who has access to what. Um, but prior to that, I worked at a company called CoreOS, which is really known for kind of pioneering the container and cloud native movements. And alongside Docker, CoreOS was kind of like the major company that kind of brought containers to the mainstream. While I was there, I worked both on scaling out kind of SaaS products running Postgres and MySQL. So I have a really good understanding of the internals of those systems from that experience. But also, CoreOS built a database that had a particular type of consistency level called linearizability that we'll cover later. So I also kind of worked deeply with consistency models. And ultimately, etcd actually became the underlying data store that's used for Kubernetes. So out there, everyone running Kubernetes is also running etcd, and maybe I'll cover a little bit about why that matters for that use case. So, what is consistency? Um, if you're familiar with databases, you may have heard this term ACID before. That stands for atomicity, consistency, isolation, and durability. Some folks say that the C was originally made up just to make the acronym work. Whether or not that was the case when they made up this acronym versus how it's used today, totally irrelevant. Today, it's very much so a real thing, and it's one of the things that people care about the most because it's the thing that people are actually uh, using to kind of design trade-offs and make trade-offs in the systems they're designing versus a lot of the other properties are kind of fairly standardized among databases. So there's a lot of ways you can define terminology. I think, especially when it comes to computer science research, you can get pretty deep. But what I think is most important is kind of covering terms in the way that everyday engineers kind of talk or how software developers communicate with each other. So, my definition for consistency, kind of using that philosophy, is the contract for how data can actually be observed. So, when developers are building systems, there's kind of these three different systems at play. There's the domain that they're working in. So, say you're building like a healthcare application or a financial application, right? A banking application. The domain is like that logic around finances or doctors and patients, things like that. Then you have your application. That's the code that you're writing. And you're going to be making assumptions about your domain as you're writing that code. But you're also going to be making assumptions about the third system, which is the place where you're storing your data. And there are fundamentally guarantees that your database is going to be providing you about how you can actually observe and interact with that data. And if at any point in time in between those three, one of your sets of assumptions mismatches with reality, that's where things start to go really wrong. If you're lucky, you'll get errors. If you're unlucky, you'll just actually have data that is effectively corrupted. It never followed the assumptions that you needed for either your domain or the assumptions you're building into your application. So that could completely create invalid data for your entire data set. So these things are really bad. And when that happens, your data is invalid, which means you might have to restart from scratch from all of your data, depending on what you're working on, or you might have to choose a completely different database technology and completely re-architect your application. All of which very, very big changes that you have to make to your code base. So, giving like a little bit of an example just to make this concrete, because that's fairly abstract what I just talked about. I'm going to give this example of a parent supervising a child purchasing something from a shopping cart. Um, and what is going to happen is a child is going to read the shopping cart. They're going to look inside the shopping cart, see the item was already in the shopping cart, and then they're going to purchase the item. And then the parent supervising everything is going to check out that shopping cart and see if the purchase took place or not. And what's really important about this is if you're modeling the system, uh, basically, this is the ideal scenario. What is It's actually probably the most unlikely of all the possible scenarios that are going to execute. What is far more likely is this scenario, which is there's going to be some interleaving of these events. The child opens up the shopping cart, and then the parent opens up the shopping cart. And then the child buys the item, and then the parent happens to buy the item because when they loaded the shopping cart in the first place, the child hadn't performed the purchase yet. So there was kind of like nothing informing the parent that they needed to like refresh the shopping cart after the purchase took place. Um, and so this kind of double purchase took place. And that's totally undesirable behavior in the system that we're modeling. So that's the most likely scenario. And there's kind of one important thing to note here is that what's happening is the purchase decision is actually dependent on that shopping cart view. So reading the shopping cart as a dependency is a dependency of actually making the purchase. Um, because computer scientists like to sound smart and use terms from physics, this is called causality or a causal dependency. But really, what it just means is that dependency, that data dependency between you have to have read this to ultimately make the decision to perform this following action. Um, Now, one solution you might be thinking about is okay, what if we take everything with causal dependencies and smash them into one event that takes place at once? That would actually be largely talking about atomicity inside of these database systems and with using the ACID terminology and a little bit of isolation in there as well. Um, but that's not actually kind of covering consistency. And that's because um, in real world systems, not only is there this ordering of the events as they take place, but this additional factor that is talking about the visibility by which when changes are actually viewable by other folks operating in the system. So here I've kind of combined the child's operations all into one atomic procedure. So they're reading and buying all together. And I have the parent still broken out. I think that helps just to help understand the interleaving, but it doesn't matter if I had that also combined to be one atomic event. Um, I have this item on the bottom of the timeline, which is when the child's purchase actually becomes visible. It's quite possible that that could happen even after the parent performs the read or an atomic read and buy. And that is, you might be thinking like, hey, I've never heard of this visibility thing. Like, what is that? How is that even possible? But you probably have heard of this. You've only probably been thinking about it when it comes to read replicas, when you have a leader and a follower kind of set up in your database architecture, and you're streaming asynchronously changes to the follower. Um, you don't always have the most fresh data to work with in the view that's queryable from the follower. So that's probably intuitive that this scenario can happen in that case. Um, However, this also happens on single node deployments of databases like Postgres, because there's a time at which a transaction is being committed to the system and when it becomes visible at the query layer. And so that, while the window is way smaller than something asynchronously replicating across the network, is still a real scenario where visibility is impacted and you can start making these types of errors in your system. Great. So now we understand the basics of consistency. I have this kind of eye chart on the right I don't think you need to worry too much about it other than just understanding that there's kind of a hierarchy of talking about the guarantees that you get at different levels um, that are kind of modeled um, so people can pick the right systems that provide the guarantees that they need. Today, what is really important is to just look at the top three and note that strict serializability, which is what we're talking about, is literally at the top. So today we're just trying to get Postgres to actually be as consistent as we know how to model in computer science. Um, there's kind of color coding and things going on there. That's not super important for what we're talking about, but it is kind of talking about like the roughly failure domains when you choose these types of models. Um, so, what actually is strict serializability? Well, strict serializability is basically the idea that your database, you can kind of group it all together as one object, and that every single transaction that happens on that database object has a strict ordering, and every transaction that happens can see the results of the transaction that happened before it. So the idea of having that total ordering is what serializable means or serializability means. And the idea that you have this visibility of the thing that happened before you is the real time constraints that you get out of a system that is linearizable. So that's kind of why these two come together to give you this kind of comprehensive total ordering where everything is visible one after each other. All right. When would you need this? And why did SpiceDB need this? So this is the thing that's going to vary greatly depending on what you're working on. For SpiceDB, because our domain, our business domain, is authorization logic, we actually need to solve a certain class of errors that can happen when a user is revoked access from a particular resource. And after that revocation, if they were basically evaluated with a stale permission, they could see new content. So that is a security vulnerability fundamentally in the system. I don't want to get into too many details about the domain just because it's not super relevant. But needless to say, our domain has this requirement that is based around kind of revocation. And if you use a stale view of the system, someone could potentially see something they otherwise shouldn't. And when it comes to authorization and permission systems, that is the name of the game. If you can't build a system where you can guarantee that folks can only see the things they're supposed to see, then you failed to build a secure system. So we fundamentally need this to solve our problem in our domain, which means we need it just no matter what we were doing, we would actually have to solve this problem. Now, how does SpiceDB relate to Postgres? That's a great question. Um, Lots of databases have this storage layer abstraction built into them. And Postgres and MySQL are no exception to this. They usually work by having an underlying key value store that persists things to disk. And that's usually pluggable to some degree. Um, and what happens in SpiceDB is we also have a similar layer. But instead of plugging it into key value stores that persist things to disk, which we totally could, instead, what we do is we actually persist that data, similar data, to external databases over the network. Um, why would we do this? This seems kind of crazy, right? The value you really get out of that is folks can then run SpiceDB and point it to a managed cloud service already providing like managed Postgres. So then they don't have to run another stateful service and they can just kind of get that managed database experience for free. Um, that gives us some unique requirements, like we can't use custom Postgres extensions. We can't write custom code and extend Postgres because we need guarantees that whatever strategy we're going to use to get strict serializability has to work across all of these different cloud implementations that don't allow people to install custom plugins and often aren't even built on the same core storage engine that Postgres itself is implemented with. Think of things like Aurora on AWS, which ultimately underlying everything is still DynamoDB at its core. So um, that is kind of the overarching challenge that we had, um, and then kind of just making this very concrete. One of the APIs that SpiceDB has is literally a change feed where we publish updates to our consumers in order. So fundamentally, we have to have everything in order and in real time so we can publish these results to the consumers of this API. Great. All right. So how did we even start approaching this problem in the first place? Well, we kind of looked at what was available to us. And Postgres actually supports serializability built into the core engine. So we could reuse at least Postgres's ability to order things. But that wouldn't give us that real time visibility, that linearizable aspect. So what we ended up doing is saying, hey, we can't use transactions as they're built into Postgres, like natively. What we have to do is implement our own abstraction around transactions. So naturally, we created a table in Postgres called transaction. And what we ended up doing is storing effectively a primary key in there. And that is because that gets auto incremented by the server, that gives us a total ordering. And then we basically manage what's called our own MVCC layer, which is multi-version concurrency control. This is a common design pattern for databases. And in fact, Postgres has its own implementation of this under the hood. But what we're doing is basically just keeping track of living data, data that has been deleted at different versions. So we keep track of the transaction at which data is created, and then the transaction at which data is deleted. And then we have to do that all ourselves. Users of Postgres normally would just get this for free because it's an abstraction provided by Postgres. But then there is this overhead, which is the vacuum. When you have deleted data and it gets very old, you can't just keep building up this data. Eventually, you run out of disk space. So what Postgres does internally for its MVCC is it has the vacuum process that every so often runs and cleans up very old dead things. So with this strategy, we have to implement our own form of vacuum or garbage collection where we go through as well. So that's one of the trade-offs is that overhead. And it's not built into any data store. We have to build it into SpiceDB. So SpiceDB has to be aware of how to clean up Postgres. So this strategy actually works, and it works pretty well, but our larger customers started having throughput problems a couple months in. So this was not going to be a long-term strategy that was going to work for us. So ultimately, we started to stare at the Postgres documentation to figure out, okay, what else can we actually do to solve this problem? And ultimately, what we did was we found this extension called pgexact. And pgexact is built into Postgres. It ships by default. And what it does is it is basically metadata storage around transactions and snapshots in Postgres. What's most important about that is not only is it keeping the stuff on disk, but it also gives you built-in functions in the query language in SQL for you to be able to probe at these things, ask questions about them, and understand them. Um, so I kind of have this some examples of those on the right-hand side here. But what's really important here is to understand the primitives by which we are working in Postgres. Every single time you query Postgres, you're viewing a snapshot. And a snapshot is actually a collection of transactions. A range of transactions occurs at any particular snapshot. And so we have this representation in Postgres, which is basically three sections separated by colons. The first section is the transaction minimum. This is the minimum transaction that went into the snapshot. And then we have the maximum as the next value. And then finally, we have in progress transactions. So these are transactions that would fall in that range in between that min and max, but actually haven't completed yet. So these are exceptions inside that range. And then what's really important here is that Postgres actually gives us this nice function that actually tells us if a transaction is visible within a snapshot. So we can actually provide a transaction and a snapshot and ask Postgres, hey, can you see this inside of this snapshot? That's going to become super, super critical in the next section. So our idea was fundamentally to take these components, now that we have these primitives, and replace our own bookkeeping, keeping track of what a transaction is, with the internals of Postgres. Now that we can poke at Postgres and understand what its transaction IDs are and what snapshot we're working with, we can actually keep track of those and store them in our transaction table and use that as our handle to understand the overarching system. And then when we're talking about the creation and deletion of our tuple data, we can just say, we can reference the transaction ID instead. And the nice thing is we can use server defaults. So we can say, by default just give me the current transaction ID and just give me the current snapshot. And when SpiceDB is actually talking to Postgres, it doesn't have to like figure out what those are and insert them into the table. You might be wondering, why do we need like the snapshot ID or the snapshot values if we have the transaction ID? And that is actually because what we're going to ultimately do is synthesize our own custom snapshots. So we're actually going to take that snapshot, which was the view of the system when the transaction executed, and then we're going to take our current transaction and we're going to insert it into that range to say this thing is marked alive. This transaction is visible. And by doing that with every single one of our transactions in that transactions table, we can actually create a state of Postgres for each transaction in between each snapshot. So that's what's getting us our total ordering that we couldn't get before. Um, the total ordering of each transaction flowing through the system. So the nice thing about the PG is visible in snapshot SQL built in is that we can actually provide both sides. We can provide the snapshot and the transaction. So by doing so, we can actually synthesize these snapshots with our transaction marked as visible inside of it, and then pass that into Postgres and use that as a filter. Because we're not relying on saying, give me a real snapshot coming from Postgres. We can actually just create our own and tell Postgres, this is what the snapshot should be, and tell me all the things that are visible in this snapshot. So we're doing some pretty tricky stuff there, but it actually makes it really simple when we're trying to just filter what's dead and are alive, because we can just say, is this visible in the snapshot? We just add a nice where clause to the query of just pulling out the relationship data, the tuple data. Um, Now, what's really, really interesting about this is the watch API I was talking about before, where we have the change feed publishing things in order. To do that, ultimately, we rely on one more bit of functionality from PG Exact, which is something that you actually have to enable ahead of time. So you have to, when you start up Postgres server, say commit timestamp equals on. But afterwards, what happens is the time at which every transaction is committed to the write ahead log is stored as well. So by having that timestamp um, associated with the write to the wall, we have this total ordering there as well, because only one thing can be appended to the wall at a time. So that all of Postgres has this kind of serialized order of events that is deterministic and stored inside the wall. And this is really giving us a hook to grab that and understand when the transaction was exactly committed. And by doing that, we can just actually slap on an order by on a query that is fetching basically all the new revisions that happened after a particular snapshot. So the last time we published the change feed, we did it at this particular snapshot. Now we have this particular snapshot. Give me basically tell me all the things newer than this. And then we run this query and we just sort it by the time it was actually committed to the wall. And that gives us our total ordering. So that's kind of the secret sauce to getting that full total ordering out of the system. Now, how far has this taken us? Right before I said it only lasted a little bit with our naive implementation. Well, this implementation has actually been tested on the largest Postgres instance size on Azure, and it still operated totally fine. So we're pretty confident that this is one of the better ways we could get this functionality out of Postgres. But that's not to say it has no trade-offs. One of the things that's really important about this is the transaction ID counter, the thing that's actually incrementing what transaction IDs are there. That's not something you can set. So if you were to PG dump all of the data from one Postgres instance and then load it into a new one, instead of starting at the transaction ID of the last time you kind of inserted data into our tables, you would start at a very low number, probably like 1, 2, 3, 4, instead of 10,004. Um, so there's no way to actually just set this counter and say, hey, this counter should be like the minimum number we see already inside of our transaction table. So we actually just have like a little SQL script that uses the procedural language in Postgres to just do a for loop and just increment this. We basically create a transaction and roll it back in a loop. And that's just the fastest way that we can actually get that counter bumped up to the value where it's going to be valid again. So that's kind of an annoying gotcha that takes place in what is often a very sensitive operation when you're doing a backup and restore. You could be doing that in a very sensitive kind of outage scenario where there's a lot on the line. So we understand that is kind of like a very, very painful edge case. The other thing to note is that basically transaction IDs have the capability of overflowing. They're just 64-bit integers. And actually, we're lucky that we started the implementation when we did, because in older versions of Postgres, they're actually 32-bit integers, and this was way more likely to occur. Um, but this isn't a problem unique to us, because the transaction IDs are actually being used internally by Postgres. The Postgres developers themselves have to solve this problem. Um, and so what happens is, to avoid overflowing that number, what happens is every 2 billion transactions, the vacuum process runs, and it effectively freezes sufficiently old transaction IDs. And in older versions of Postgres, this freeze was actually just replacing the transaction ID with a magic constant. But I think in more modern systems, how they work is they actually keep like a secondary kind of table that just marks these values as special. Now we're lucky we don't actually have to create any additional logic around this, because our domain of authorization data, as things become stale, as permissions become stale, they become irrelevant to these systems. So we actually can just run our garbage collection, our own vacuum process, way more frequently than how often Postgres is running, and can effectively guarantee that you will never be in one of these scenarios, regardless of just how much writing you're actually doing to the system. So we actually just kind of lucked out that our domain enabled us to never even be close to this particular scenario. Cool. That's all I have for y'all today. I just want to shout out to the authzed engineering team. Jake, actually the CEO and one of my co-founders of authzed, created this initial design. I really want to thank the Postgres documentation maintainers. Without that, we would have never been able to discover this strategy whatsoever. PGpedia is also a super useful tool once you know what you're doing with Postgres and you just want to share, like, how does this function work, or what does this particularly do. Great tool to just share that with your share that knowledge with your coworkers. And then I want to thank Kyle Kingsbury, who created kind of Jepson and all the consistency content I have. That graph that I showed you, modeling the different models and how strict they are. That is all content based by him. He actually does a service where he will consult for folks and test that the consistency guarantees of their database that they advertise actually meet reality. Um, so he has a great source of information, just of understanding the different trade-offs that go into these database systems. And then I want to thank the organizers of the conference for letting me talk on this topic and organizing such a great event. So thanks, everybody.